Hello, good morning, everyone. Welcome to my section. I'm Dr. Guanjie He. I'm the senior lecturer in chemistry from the School of Chemistry at the University of Lincoln. And for today's talk, I will talk about some chemical method to improve the next generation energy storage and conversion technologies. So in today's talk, I will have a brief introduction about our school, our research group, and some recent progress related to the materials innovation for the clean energy applications. So when we talk about chemistry, do you have any ideas about the definition for chemistry? And chemistry is actually the scientific discipline involved with the elements and compounds composed of the atoms, molecules, and ions. So their composition, structure, properties, behavior, and the changes they undergo during a reaction with other substances. So actually in the scope of its subject, the chemistry occupies an intermediate position between the physics and also the biology. And it is sometimes called the central science because it provides a foundation for understanding both the basic and applied scientific disciplines at a fundamental level. So for example, the chemistry explains the aspects of the biology. That is a biologic chemistry, right? And it can also explain the plant chemistry. That is what we call the botany. And we can know through the chemistry about how medications work. That is pharmacology. And we can definitely know some insights from the chemistry knowledge about how the environmental pollutants are degraded. So that is ecology. And how can we collect the DNA evidence at a crime scene? That is a forensic science. And of course, the chemistry has a very close relationship with the material science and engineering. We can use the chemistry knowledge to guide our materials design. For example, the nanomaterials design. Yeah, they can give us the knowledge about how can those materials be produced or generated. Yeah, when we talk about the School of Chemistry at University Lincoln, I'm very honored to announce that the chemistry subject table Lincoln ranked number 2 according to the Guardian University League Table 2020. And our university also did a very good job. The Lincoln ranked number 17th according to the Guardian University League Table 2020. And our university also received the gold medal according to the Teaching Excellence Framework. So our school is located in this Joseph Banks Laboratory. And Joseph Banks Laboratory is also the home to the University of Lincoln's Pharmacy and Life Sciences Research and Laboratory facilities. So the university chose to locate these schools at Lincoln Science and Innovation Park rather than on its neighboring campus in order for its researchers and the students to be part of the park's scientific community. And in the JBL, the Joseph Banks Laboratory, we have the world-class equipment and the access to the scientific equipment at JBL is available to the science park tenants. And this includes the X-ray diffractors and nuclear magnetic resonance. And we have different microscopies, including the optical microscopies and electron microscopies. And within the JBL, the technicians, academics, and the researchers work with science park business to share their skills and knowledge and try to undertake research and collaborate on different projects. And we are quite excited about the recent investments. We are trying to build up the Bridge Advanced Engineering Research and Development Center. And this is a collaborative scheme funded by the European Regional Development Fund, the Greater Lincolnshire Local Enterprise Partnership, and also the University of Lincoln. And our school plays a central role in leading the development of the Bridge Lab. And we will work closely with School of Engineering and our industrial partners and try to advance the development of our materials and the techniques and try to find the commercialization routes for such techniques. And when talking about the research and the innovation at our chemistry school, we are divided into 3 different research groups. The first one is the Advanced Functional Materials group. Because I'm the lead for this research group, I will later talk a bit more in detail. And in the Advanced Functional Materials group, we try to pursue the insight into the design and the development of materials across a different landscape to address the future application. And the Chem Biointerface group, our colleagues work in collaboration with medicinal chemists and also the biochemists in the schools of pharmacy and life sciences. And they try to pursue the insight into the design and the development of bioactive molecules and their effects in organisms and also the biospheres. As for the analytical methodologies group, our colleagues try to address the cutting-edge challenges requiring design and innovation of analytical technique for complex materials, challenging measurement scenarios and changing the societal context. Now let's focus on a little bit more on the Advanced Functional Materials group at our school. So as for the Advanced Functional Materials Research Group, we try to use different synthesis methods, the characterization and the application for the different functional materials, from the development of novel synthetic methods to transform the small molecules, to the systematic design and development of materials beyond the molecules that creates the nano and the micro-size assembly for a wide range of the application. So according to our research directions, we have the different sub-research aims. The first one is about the supermolecular materials and the energy materials and the electrochemistry. So I will talk more related to my research later. And so we also have the colleague working on the catalysis and the green chemistry, the historic and the conservation materials. And we also have the strong research team related to materials simulation and materials characterization support. So our research group member occupies more than 10 academic staffs from the School of Chemistry. As for the energy materials and the electrochemistry, we try to focus on the molecular inorganic synthesis, the biochemistry and the solid-state synthesis to fabricate the electrode materials for the next generation batteries, and also the electrocatalysis. And you will hear a lot about the batteries and the different electrocatalysis later, for clean energy application. For example, the lithium batteries, the zinc batteries, and the supercapacitors, the electrocatalysis for CO2 reduction and the water splitting. We generate the electrocatalysis to split the water to hydrogen and oxygen. And our colleague also try to develop the electrochemical method for the chemical analysis. So as for the catalysis and the green chemistry, our colleague aimed at developing the new routes for the conservation of the small molecules, for example, the carbon dioxide, the cellulose, into the useful intermediate chemicals and ultimately the end products through the advanced catalysis. So as for the green chemistry and the green chemical engineering, they require the major breakthroughs, especially the breakthroughs in catalysis. and try to make the new reactions processes not only the environmental benign, but also the economically valuable. So as for the historic and the conservation material, we have colleague focuses on the underlying chemical and the physical chemical processes that affect the degradation and the sustainability of heritage assets in a changing environment. So the key areas of research fall into three categories, including the understanding decay mechanism, designing new conservation materials, and develop new methodologies for professional practice. As for the material simulation, our colleague focus on computational modeling of condensed matters and try to understand the electronic structure from the density functional theory, and also try to understand the catalytic behavior or the electrocatalytic process at the atomic scale. And the materials they are interested in, like the carbon, metal oxides, and the surfaces, vibrational properties, and also the superconductivity of different type of the materials. So as for the supramolecular materials, our colleague tried to develop the rare earth containing assembly to make the alternate copolymers. And they also use self-assembled molecular materials for like the energy applications, the antimicrobial properties, and try to understand their bioproperty. And we also have a very strong materials characterization support team to support our materials research. And our colleague also try to develop the different methodologies for in situ and ex situ measurements of functional materials. And we have different instrumentation, which includes the modern NMR, the different X-ray diffraction, the thermal analysis, and various spectroscopies. And we can combine them together with the thermal analysis as well. And we have the SEM EDS, the gas chromatography, the mass spectroscopies in our group. And now here's a brief introduction about our research group. Let's focus on today's topic, the energy storage and the energy conversion. So when we talk about the energy storage, I believe all of you will know that we need the energy storage devices and technologies in all aspects. From the electricity generation, for example, like the traditional methods, the power plant, and also the clean energy, like the wind power and solar PV, to the usage, including the residential area, the industry, and also the transportation, the electrical vehicle, the EV, for example, right? We expect those energy storage devices to be powerful and long-lasting, but actually they are easily died. So for our task is try to use advanced materials chemistry to save them. And there's one frustrating problem we may encounter every day, that is my phone is out of power, right? We may lose contact with our friends easily. And there's also another phenomenon maybe you have already noticed. When we get a new phone, right, during the first year of the usage, you can charge it, use it for 1 day or even 2 days, right? But during the second year of the usage, probably you need to charge it every day. But during the third year, fourth year, or even fifth year of your usage, probably you need to charge it every half day. So that is quite frustrating. And this is mainly due to the issues with the stability and the capacity of those batteries or those energy storage devices. As for the stability, it is quite easy to understand, right? That is just the decay of your materials, decay of your devices. So what about the capacity? The battery capacity is actually a measure of the charge stored by the battery. And the battery capacity is determined by the mass of the active materials contained in the battery. And sometimes we also use the mass of the whole device contained in a battery. And the battery capacity represents the maximum amount of the energy that can be extracted from the battery under circumstances. So the more capacity, the better, right? This is of course. So to save this issue and prevent our losing contact with a friend, the power bank is generated. So we call it the bank. You can see how important it is for our daily life, right? But this is one typical type of the power bank. You can see those power banks are quite thick and also heavy. And so we can a little bit hard to adapt it in a little small purse, right? And so can we try to make it a bit smaller or a little bit lighter? Yeah, so that is a problem related to the capacity and also the energy density related to the energy storage devices. So we just discussed about the capacity definition. So the energy density is the amount of the energy in a given mass or a given volume. If we just consider the capacity equals to the quantity of the electric charge. And for the energy density, you can see that is the capacity times the voltage range, right? And another definition is called the power density. So the power density can evaluate how fast the energy can release. So I will compare both the energy density and power density for you later. And if we try to compare the energy density, yeah, that is total energy over the mass or the total energy over the volume, right? And same as power density, that is total power over the mass or the total power over the volume. So we expect those energy density and power density, the more the better, right? We can either increase the energy it can store or the power it can release or reduce the mass or the volume, right? To increase the energy and the power density. And there's a very interesting and the commonly seen plot, the Reagan plot. We use the Reagan plot to describe the relationship between the energy and the power densities for different energy storage devices. As you can see, for the capacitors or supercapacitors, they have very high power density. But for the energy density, the batteries and the fuel cells, they have more energy density. So the power density is more likely to be the spirits. That means the energy can release very rapidly if a high power density is achieved. But for the energy density, that is more likely to be the marathon. But for the material scientists like me, we try to improve the materials to exhibit both the high energy and also the high power densities. Yeah, try to boost their development in these directions, increase them simultaneously. Yeah, by using some materials innovation to try to increase them. And also we need to tackle the poor stability issue of those electrode materials by using some materials and the structural engineering strategy to solve them. And as for our materials design, yeah, we also need to take into account of the cost, the safety, and also the mass production of those materials, right? So here's an overview about my research strategies like 2 to 3 years ago, but I still use this strategy for another application. I combine the materials design with the inorganic chemistry synthesis and try to develop different electrode materials for different energy storage applications. And I use the wet chemistry method like the hydrosomosynthesis, the electrode deposition, the sol-gel method, and also the thin film fabrication techniques like the chemical vapor deposition to deposit the materials directly on the current collectors. So what is this process mean? That means we can form the self-standing electrodes. As for the commercial or the traditional electrode making process, we have these active materials, but those are in powder. We need to paste them by making the slurry with a binder and paste them on the current collectors. And this process is relatively time consuming. And also we need the extra equipment to do that. And my strategy is try to form the materials by form the strong bonding with current collectors and form the composite materials directly with the current collector. So I have developed different nickel tungsten, the cobalt tungsten materials on nickel form for the supercapacitor application. Yeah, try to realize high rate performance, high power density. And I also developed different nickel tungsten materials. Firstly, claimed their merits for the supercapacitor application. And I also developed different nickel cobalt sulfide materials in the self-standing electrodes and use them in the aqueous energy storage devices. And from the kinetic view, I try to prove they work as a battery type. And I gave them a new term, the alkaline rechargeable alkaline batteries for such energy storage mechanism. And by combination and collaboration with the in situ characterization technicians and also the theoretical scientists, I developed different self-standing electrodes as cathode materials for the lithium-ion cathodes. And we realized very highly stable cathodes for the lithium-ion battery application. So when we mentioned about the energy storage devices and batteries, probably the first example you can think is a lithium-ion battery. And the lithium-ion battery occupies a large proportion of the global energy storage or the battery market. And you can see it increases quite sharply with a CAGR of around 11%. And the global battery market for the lithium-ion battery can reach around 73 billion US dollars at the year of 2025. And if we look at the battery mechanism, the energy storage mechanism about the lithium-ion batteries, it is quite simple, to be honest. Let's try to use a simple cathode materials, the lithium cobalt oxide as an example. So during the charge, the lithium can deintercalate from the lithium cobalt oxide to the electrolyte. And as for the anode material, we usually use graphite material or the lithium metal as the anode. And during the charge process, those lithium can intercalate it into the graphite materials. Yeah, and if for the discharge process, the reaction is a reversible one. So for the overall reaction during the charge and the discharge, that is just the lithium intercalated or deintercalated into the electrode materials. But the lithium batteries has some drawbacks, and also it has a huge advantage. Let me try to present to you now. And our research tried to focus on another type of the batteries, the zinc batteries. Let's firstly have a comparison about the lithium and the zinc batteries. So for the lithium ion, the charge carrier is this lithium 1+, right? And the atomic weight, it is quite light, so that is quite good. Around the 7 gram per molar. And also the lithium has a very suitable potential range, that is a -3 versus the standard hydrogen electrodes. That means it can give a relatively wide potential range. But in order to reach this wide potential range, we can only use organic electrolytes. And as for the theoretical specific capacity and also the volumetric energy density, the lithium battery is quite high. But if we try to consider from the cost, the metal cost of the lithium is relatively high. That is around the $19 per kilogram, and the abundance is relatively limited. So some scientists are trying to develop the sodium-ion batteries and the potassium-ion batteries because they have the similar properties, but just relatively larger ionic radius and atomic weight compared to the lithium-ion battery. And they also have a suitable standard potential. Yeah, they can use in the organic electrolytes. But I believe most of you have heard about the accidents, about the battery explosion. For example, the battery explosion from the mobile phones and also from the electrical vehicles. And so those explosion happened mainly due to the short circuiting of the batteries. And because you use the organic electrolyte and that is flammable, so the explosion happened. On our group recently, we try to focus on the zinc-ion batteries. But if you consider the atomic weight, that is not that suitable, around 65. It is relatively heavy, right? But for each zinc, it can provide the 2 electron charge carriers. And also, what is permitting is that the standard potential for the zinc versus the standard hydrogen electrodes is minus 0.76. That is suitable for the aqueous energy storage application. And also, as for the volumetric energy density, the zinc is good, and especially for the metal cost, that is very cheap, just around $2 per kilogram. And if we use zinc directly as the anode, it can work in the aqueous electrolyte. So that is perfect. And our group has developed different flexible zinc-ion batteries. We use hydrogel as the electrolyte. So you can see those devices, you can easily bend it, fold it, but there's no explosion, even if there's a short circuiting happening, but there's no explosion, right? And we can simply integrate them with other flexible electronics. And we also try to use a hammer to hit it, and you can see those batteries work quite stable. And due to the high atomic weight of the zinc, and also there's a 2 electron charge transfer. If we use the aqueous electrolytes, there might be some problems related to like the polarization, and the hydrated zinc ions is relatively large, not like the ionic radius as shown here. And we try to develop the suitable cathode materials. This is one of the major research direction in my group. Yeah, and so for the suitable cathode materials, we have the layered structures or ternary structures, and they might be the zinc host, but the reaction might be sluggish. So how can we improve the reaction rate? They can store it easily and it goes back to the electrolyte easily for those zinc ions. In this work, we try to compare, firstly, different V2O5s, vanadium oxides, polymorphs, and try to provide the evidence about the suitable cathode host structures. And we also did a lot of experiments related to the electrochemical performance evaluation and the materials characterization to find out the suitable pre-intercalated ions. And we find out this phase, delta nickel 0.25, A205 can work as a stable cathode host. And the stability is quite high. The capacity retention is over 98% over the 1,200 cycles charge and discharge. So that means we charge and discharge the batteries continuously for over 1,200 times. And the specific capacity is quite good. That is over 400. That's a low current density, 0.2 amps per gram. And so we also try to evaluate the capacity at the different current densities to evaluate the rate performance. So what does the rate performance mean? Maybe you have already heard about the fast charging batteries. Probably we can charge our mobile phones for 20 minutes and then use for half a day or even 1 day. That means we need the fast charging batteries. And if we use a high current density to charge our batteries, firstly, we need to consider the safety issues related to that. Will the short circuiting happening? And the second one is how much charge we can put in these batteries compared to the low battery charging rate. And the rate performance is to evaluate such parameter. And so we also did a lot of collaboration with theoretical scientists, and so also we did a lot of tomography evaluation and the beam time evaluation about our electrode materials. So I won't mention too much technical questions here. And the conclusion with this here is we discussed and discovered the different type of the host structures and the pre-intercalated ions. We find out the different types are quite important for a stable cathode materials in zinc batteries. And our developed electrode materials has effective diffusion coefficient that is much better reactant transport capability than those in the commercial lithium batteries. So from this work, we try to discuss a different cathode host and the importance of the type of species for the pre-intercalated ions in the cathode materials. And we think over another question, can we try to generate rich deficiency cathode materials with a lot of hollow structures or porous structures to facilitate the zinc intercalation, and also our structure need to be stable. And after this, we try to develop another type of the cathode materials. That is the oxygen deficiency of the vanadium bronze cathode materials. Yeah, we try to induce different cations like the ammonia ions and also the water as a lubricant. And also we try to generate the oxygen deficiency to increase the electron conductivity. And you can see from the electron microscope structure, just from the one-step synthesis, we can make those porous structures. So that means cathode materials can have a good interaction with electrolytes, the species in the electrolytes. And so these materials can work quite stable as a zinc cathode. We showed a much improved capacity of 430 milliamps hour per gram. And so also compared to the first works, the rate performance increased a lot. And you can also realize the stable capacity retention. That is over 95% over the 1,500 cycles. And from this work, we develop a new material, and that shows the improved performance by synergistic effects from controlling pre-intercalated species and also the tailored oxygen deficiency. And following this work, we try to understand, will the amount of the pre-intercalated species influence the final structures or final performance? And we did the third work related to our cathode design. And by using the wet chemistry synthetic method, and we have successfully prepared the controllable amount of the intercalated ions in the manganese oxide matrix. And one is with potassium 0.28, and another one is 0.21. So if for our traditional understanding, the one with less potassium ions might be more stable, right? Due to more potassium ions, they may occupy more host structures for the zinc ions, but our results shows a controversy result. And we showed the potassium 0.28, the higher amount, shows a better performance and the rate performance and also the competent cyclability. So we try to understand this phenomenon. We did a lot of collaboration with theoretical collaborators, and we discovered there's a threshold about the potassium and the manganese atomic ratio that is around 0.26. So the potassium ions can suppress the structural transformation by stabilizing the initial structures for the manganese oxide. That's why it can realize a very stable performance. Yeah, so now let's try to move to the energy conversion. So do you have any ideas about what is energy conversion? Actually, this figure shows what is the energy conversion, right? We can use the solar panel to do the water splitting. Yeah, use the renewable energies, for example, like the solar panels, and to use the splitted hydrogen to power the fuel cell cars or for the home use. And actually, the materials chemistry is a bridge between the energy storage and the conversion applications. As for the energy storage and the conversion, they have the similar materials design and engineering strategy. For example, we need to increase their surface area. We need to try to increase their electronic conductivity, right? We need to try to increase the active sites for the host structures. And by developing both energy storage and the conversion devices, we can finally realize the zero emission targets. Actually, the metal air batteries is a representative for the integrated energy storage and the conversion devices. And another major area in my group is about developing different zinc air batteries. So I have already discussed the advantages for the zinc anode. What about using the air at the cathode? Yeah, that is much cheaper compared to the metal ion batteries, right? And as for the zinc air batteries, they have the low toxicity. And as for the discharge voltage, they have the very flat discharge voltage. That means it can give the output voltage quite stably. And as for the zinc air battery, they have a long shelf life. And as for this type of the battery, they are of the low cost and they have the high energy density. We can make the zinc air batteries to power the electric cars, and also we can make them to power the very small hearing aided devices. But for the commercial zinc air batteries, that is a one-time use battery, so we can only discharge them and throw them away, right? We cannot reuse them. So how can we realize the rechargeability? One pioneered work from Stanford, they developed this 3 electrodes configuration. So during the discharge process, they connect the zinc anodes with the oxygen reduction catalysis. They use the cobalt oxide on the nitrogen doped carbon nanotube for the oxygen reduction process. But during the charge process, they connect the zinc anode with oxygen evolution catalysis. They use a nickel iron double layer hydroxides on the carbon nanotube as the oxygen evolution catalysis. And this 3 electrode configuration can realize the charge and discharge process for the zinc batteries. But those are not for practical use. And for all of our batteries, that is 2 electrodes, right? We don't need to change the electrodes during the charge or the discharge. But it is quite clear, right? In order to realize the rechargeability, we need the oxygen reduction catalysis and also the oxygen evolution catalysis in one system. And actually, the oxygen reduction and the oxygen evolution are conflicted to each other because they are the reversible reactions. This is like the Chinese ancient philosophy, yin and yang. Have you seen this cartoon before? So how did this fat panda become the dragon warriors and fight against the enemies? And he knows how to balance the yin and yang. Yeah, we need to balance them in one system. So inspired by this, we have developed a single material that is a manganese cobalt oxide on carbon nanotubes. And they can use as a bifunctional oxygen electrocatalysis. And in this work, we just evaluate their catalytic performance. As for the kinetic behavior, they are still infrared compared to the commercial noble metal materials for the oxygen reduction and oxygen evolution. That is PT on carbon for the oxygen reduction and IRO2 on carbon for the oxygen evolution. And I also developed the prototypes for the rechargeable zinc batteries. I developed another series of the transition metal nitride materials. And those materials can outperform the commercial noble metals as a bifunctional oxygen electrocatalysis. And these metal nitride materials are much cheaper compared to the PT or IRO2 as well. To further lower down the price for those electrocatalysis as an air cathode, we also developed different type of carbon materials, and we did a lot of theoretical collaboration to understand the functional groups to the catalytic performance influence. And the carbon materials are also a type of the permitting air cathodes for the zinc battery use. So here is a quick summary about how we can combine the electrocatalysis design with other materials chemistry aspects. Yeah, we can combine our synthesis, right, with advanced characterization. We can combine the electrochemical performance evaluation with theoretical guidance to guide our catalysis design. Yeah, so when we talk about electrocatalysis, the most widely used are the water splitting. The water split to the hydrogen and oxygen. And we can also use electrocatalysis for the CO2 reduction. And we have a colleague in the school working on this area. And there's also another emerging area is to use electrocatalysis for the nitrogen reduction, or we call it nitrogen fixation, to generate the ammonia. And because we need to break the nitrogen triple bonds, and this process is quite sluggish and tedious, and there's much more work need to be done in these fields. So let's focus on one simple reaction. That is 2 water molecules. If we add the extra energy, we can generate the hydrogen and also the oxygen. And my group also work on the hydrogen evolution and the oxygen evolution for the water splitting devices. So here's the video you can see. For the 2 water molecules, they can generate 2 hydrogen. And you can see there's more bubbles here, right, compared to these electrodes. So this part is electrodes to generate the hydrogen. And this part is the electrodes to generate the oxygen. So if we can use a chamber or use a membrane and put them to different chambers. We can collect the hydrogen and collect the oxygen for different applications. And we connect those electrodes with another output that is a potential stars. It gives extra electricity to facilitate the water splitting. So there's a question related to that. Can we use less electricity to generate more hydrogen? Yeah, this is what we need to be done about the electrocatalysis design. And our group has reached its experience about developing different hydrogen evolution electrocatalysis. We try to boost the active sites, we try to boost the surface area, or we call the electrochemical surface area, and try to increase electronic conductivity for our electrodes design. Yeah, we need to reduce the energy needed for the hydrogen generation. And we also need to think over how we can increase the stability for such electrocatalysis. So here's a summary about my today's talk and how we can use chemistry in clean energy. And as for my research group, we try to combine the controlled synthesis with all the assembly, the surface modification, and the structural engineering, and try to develop the new materials and understand their behavior from mono materials to composite to integrated components, and finally to device innovation. And so we also work closely with the engineers to realize the real-world application. Yeah, for example, we can combine the materials chemistry with the electrode engineering, with the in situ or ex situ materials characterization, experts with device configuration, system scale, or industrial precisely experts to facilitate the development of the clean energy application. So in today's talk, I initially introduced our school, and if you are interested in the specific staff profiles, you can check our website. And I discuss about the electrode design for different energy storage devices, the batteries and also the supercapacitors. And I mainly introduce 3 different pieces of work related to the materials cathode for the zinc batteries. And I also talk about some different air cathode design for the zinc battery cathodes. And finally, I discuss about some of the work we try to generate on the hydrogen evolution electrocatalysis. And thanks for listening. And if you have any questions, please feel free to drop me the email. And if you have any questions related to the School of Chemistry, like the application or the admin and the module organization, please feel free to contact us at the chemistry@lincoln.ac.uk. Thanks for listening.